This module is an introduction to the Hadoop distributed file system, HDFS. We've divided the module into 3 lessons. Lesson 1 focuses on HDFS architecture, design goal, the performance envelope, and a description of how a read and write process goes through HDFS. Lesson 2 focuses on tuning consideration, performance impacts of tuning, and robustness of the HDFS file system. Lesson 3 will focus on moving data from HDFS, the APIs that are available for application access and for data movement. So the first video in this lesson is an overview of the HDFS architecture. So we'll be able to explain the HDFS design goals, the factors that impact meeting some of these goals, and the approach taken to meet the design goals. And then we'll conclude with a basic HDFS architecture explanation. So the key design concept was to get performance by breaking files up into blocks that you can spread out over a lot of disks and a lot of nodes. So this lets you pool data resources across hundreds or thousands of nodes and gives us a lot of throughput. And the idea was to use low-cost commodity hardware so that you could do this at a reasonable price. This brings us to factors that were involved in the design. So there's a lot of nodes and disks. So this means there's a higher probability of hardware failure. So the design needs to account for this. You need to be able to port this implementation across lots of different kinds of hardware and software, so that when you're using commodity hardware and different kinds of OSSs, you shouldn't have to make major changes to make things work. And the goal is essentially to handle large data sets, and we mean terabytes to petabytes, and enable processing with high throughput. The approach taken, there were some simplifications done to enable this to happen. So there's a simplified coherency model. The idea is you write once and then read many times, and that simplifies the number of operations you have to do to commit the writes. Data replication is the way to handle hardware failures. So what you do is try to spread the data, same piece of data on different nodes, and possibly make this rack aware so that you are resilient to single nodes failing, or even an entire rack failing, which could happen, say, if the rack loses power. The next thing to do was to move computation close to the data, so you're not moving data around. That improves your performance and throughput. Some of the POSIX requirements were relaxed to increase the throughput, and we'll see an example of this with the client-side buffering of writes in a little bit. So the ultimate HDFS architecture looks like this. There is a name node which essentially carries all the metadata, and the data is spread out over data nodes. And if you have a file that gets broken up into blocks, and these blocks are placed on the data nodes, and they're replicated among the data nodes. And as I mentioned, the replication can be rack aware. So that's the design diagram. How it works is with the single name node. So you have a master server that manages the file system namespace and basically regulates access to these files from clients, and it also keeps track of where the data is on the data nodes, where the blocks are distributed, essentially keeps track of whether the data nodes are doing okay. If there are failures, migrate the data to another data node from a copy, of course. Now, if you have multiple data nodes to get the performance, typically one per node in a cluster. So you're basically using storage which is local. You manage the storage on the data node. It does the read and write requests on the clients based on what information is got from the name node. Basically, the block creation, deletion, and replication is all based on instructions from the name node. And we'll go into more detail in how this happens in a read-write process in the third video of this lesson.